Hi everyone, and welcome to Erik's Electronics Workbench. So on the bench today I have this Hewlett-Packard 8561E spectrum analyzer that I recently acquired. Now this spectrum analyzer covers from 30 Hz to 6.5 GHz, so a very nice wide usable frequency range. The instrument looks to be in very clean condition. It does power up okay, and it's not displaying any error codes, so that's all really a good sign. And it seems to be accurate. I'll go ahead and demonstrate that in just a moment. You can see the accuracy on the display. However, I did notice an issue with one of the controls, so we'll take a closer look at that and see exactly what's going on. The control just doesn't seem to be working quite right, and you'll see that very quickly when I demonstrate the instrument. So let's get started. So before I power up the Hewlett-Packard 8561E spectrum analyzer, let's take a quick look at the front panel layout and also the back panel, just get a general feel for the overall layout of the instrument. Now, if you're familiar with other Hewlett-Packard spectrum analyzers or some of the Agilent technology spectrum analyzers, the general layout may look similar on this as compared to other instruments. For example, I have a Hewlett-Packard 8594E, and the layout of the controls is very, very similar. So it makes going between the different instruments just that much easier because of the familiarity between the location of the controls. Now, a lot of the controls on the front panel are pretty self-explanatory, but just a quick walkthrough, take a look at them. So right here we have the main power on-off control and a green LED indicator above that. The volume control, so there's a built-in speaker and the demodulation in AM or FM. This controls the audio signal. The first LO output, LO is local oscillator. So you can see right here it says terminate in 50 ohms. This is a little cap on here has a 50 ohm resistor inside of it. It's very important that be on there when that output is not in use. IF input, or intermediate frequency input. Right here, this calibration output is a 300 megahertz signal used in calibrating the instrument. You can see it says 300 megahertz at minus 10 dBm. Probe power for active probes. There's 3 little pins in here for the connector, and I do have some active probes, so that's very handy. It's a common type of connector that was used on Hewlett-Packard and other models that they made, so you can use the same probe between different models. There's actually 2 different DC voltages that are produced in here, and then there's a ground connection. Right here is the main RF input, so you can see, of course, it's a 50 ohm input, 30 Hertz to 6.5 gigahertz. And you can see the note under here, the warning, it says 0 volts DC max. So if this is AC coupled, which is the default setting, it blocks any DC input, and you can actually go a plus minus 50 volts DC and it won't harm the instrument. So plus minus 50 volts DC max. If this is direct coupled, you cannot put DC into the instrument. I think the maximum allowed is about 200 millivolts. So if you go above that, you will absolutely destroy the front end of the instrument. It will cause definite damage, and you'll have a very bad day because it's extremely expensive to repair that kind of damage. So when this is DC coupled, it will extend from 30 Hertz, or that lowest frequency of 30 Hertz. When this is AC coupled, the lowest frequency, I believe, is about 100 kilohertz. So you do lose some of that low-end frequency. So if you need to extend to 30 Hertz, you do have to DC couple the instrument. The AC coupling is the default setting because it is safer. It blocks any accidental DC voltage from getting into the instrument. Now over here, the step up and down and then this knob are just used to move through numeric values and settings. So pretty self-explanatory on that. The frequency span and amplitude are some of the main settings that you'll often use. These buttons get used a lot right here. So setting the frequency span, and then of course the amplitude on the display. I'll demonstrate those when I put a signal into the instrument. You'll see those in use. These buttons right here are for the soft key menus. So there are indications on the cathode ray tube over here on the display. And whatever is marked over here, of course, this is the button that activates that. So they're just menus that you can navigate through. Up here, the general instrument state over here. Preset is just putting the instrument into a known preset, like a starting point. The other various settings over here, I have calibration, auxiliary control. These are just in general use of the instrument. The marker is extremely important. So there's a little diamond-shaped indicator that moves around on the trace on the screen, and you move that around with this knob control. And the marker is used in taking various measurements. Again, I'll demonstrate that when I power up the instrument. Over here, the general control, you have sweep, bandwidth, triggering, auto couple, trace, and display. So again, just various settings of the instrument. And the data entry down here, a numeric keypad. And then over here, when you enter something and you need to terminate that entry and enter the actual value, you can see there's gigahertz, but it also has dB and plus dBm, megahertz, kilohertz, hertz, microvolts, so various terminations for the type of numeric value that you enter into the instrument. So again, pretty self-explanatory and very similar type of controls that you'd find on most spectrum analyzers. So the spectrum analyzer is pretty heavy. Let me move the camera out of the way. I'll turn the instrument around and then we'll take a look at the back panel real quick. All right, here we are looking at the back panel of the spectrum analyzer. And one of the first things we can see up here is that there's a calibration sticker that's still in place. It's not been broken yet, and it's overlapping from the back panel onto this top cover. No one's been inside this instrument, which is always a good thing to see. Now, I do want to open up the instrument. We'll take a look around. We'll get to that a little bit later. But it's always nice to see those calibration stickers still in place. So starting over here, we can see there's a Hewlett-Packard interface bus, or HPIB. This is for remote control of the instrument. Very common. HP had those on many, many different instruments, and that's their interpretation of the GPIB bus, or general purpose interface bus. Now right here, this video output is not a video like you would have going to, say, a television set or something like that. That video output is related to the vertical deflection of the trace, and it's a variable voltage that comes out of there. External and gate trigger input. Right here is a blanking and gate output. So this is related to synchronizing with external instruments, and also like a pen lift if you have an external plotter. Down here, this LO sweep, local oscillator sweep output. This is related to external tracking generator, and the function and what this does is related to some controls that are activated through soft menus on the front panel. Right here, this is a 10 megahertz reference in and out. So if you're using the internal standard, this will output a 10 megahertz signal. But if you want to input a 10 megahertz signal right here from an external standard, you can certainly do that, and it'll override the internal frequency standard. Of course, the AC input right here, and the voltage selector right here for the AC input. Cooling fan, of course, and then right here, this is a mass storage module. It's an option. It plugs onto the back, and there's a slot right here where a memory card can be installed. By today's standards, the memory capacity of this system is pretty low, but back in the day, it was pretty cutting edge. And it's basically for storing traces and other operating parameters that the instrument has. So let me reposition the spectrum analyzer, and I'll go ahead and power it up, and let's just take a quick look at how it's functioning and then the issue that I found. All right, let's power up the Hewlett-Packard 8561E and see how it's functioning. So I'll press the power button, and we'll get a display here in short order, and it should give us a startup screen. We do see right here, it says RF adjust status, and that's done, and the IF adjust status is working through that. So we'll give it a moment. Pardon the flickering on the camera, that's just the refresh rate on that CRT, not really playing nice with the camera. So it started up okay, no problems. There's no error codes, they would be indicated in this lower corner. You can see right here it says copyright 1989 Hewlett-Packard, but the actual revision of the operating system is 960401. So 96 was the year 1996. So it's a little bit later operating system. They were producing this prior to 1996. And as the operating system was updated, some features were added, and there were changes and revisions, of course. So it's nice to see that this does have a little bit later version. So right now this is sweeping the entire range of the spectrum analyzer. So this is 30 hertz on the left-hand side graticule over here, and on the right-hand side graticule, this represents 6.5 gigahertz. So the entire range right now is being swept. So let me grab this coax cable over here, plug this into the instrument. So this coax cable is coming from my 10 megahertz frequency oscillator. It's a GPS disciplined oscillator, so it's synchronized to the GPS time signal or time standard. So very, very accurate 10 megahertz reference, and it's basically accurate down to 100 microhertz. So I'm looking at its display right now, and it's 10 followed by all zeros down to 100 microhertz. So very, very accurate signal. So we can check the accuracy of the spectrum analyzer with this. So right now the signal is being applied, and of course we don't see really anything except over here on the left hand side. We see some kind of peaks and some activity, but that 10 megahertz is completely scrunched over to the side because this range, this sweep is so wide. So we need to put that in the center. So I'll reach around over here, I'll do frequency, Let's put 10 megahertz in the center, like so. Let's make the span, we'll do 1 megahertz, and let's get the amplitude down like so. Now ideally the amplitude on the peak of the signal that you're measuring, you want that to basically touch or be very, very close to the top graticule, which is the reference line. So right now you can see the reference line is at 20 dBm. You can see the attenuator is set at 30 dB. And then this represents 10 dB per division on this scale vertically right here. Okay? So right now you can see the center is at 10 megahertz and the span 1 megahertz. Resolution bandwidth is 10 kilohertz, video bandwidth 10 kilohertz, and the sweep time is 50 milliseconds. Now, if I come over here to the marker, so the marker is that little diamond shaped, you can see right there, indicator. So when you move the marker up to the top of that peak, see right there, 10 megahertz, so very accurate. We can see the marker right at 10 megahertz, right at that peak. The marker is indicating 13.33 dBm. So if I come over here like so, you can actually put the marker at the peak automatically. If you just do a peak search, it puts it right up there. And then over here, if I move the, let's see here, go marker to reference level. So that will put the top of that peak right at the reference level, and it's now changed the reference line to 13.7 dBm. So let's take a look at the frequency counter function. If I put marker and I just move the marker off of this peak a little bit, if I come over here to, let's see, the frequency counter right here, turn the counter on. I think it was on already when I hit the button. Anyway, frequency counter is now turned on. Let's move the counter resolution. Let's make that. So the counter resolution is now 1 hertz, okay? And we can see up here the counter right there, 10 followed by all zeros, very, very accurate. So it's reading exactly what is expected. If I move the marker up to the peak again, you can see it doesn't change the frequency counter reading. Now, you can see the display is more of a slow update because of that counter function being turned on. But if you move the marker down here into the noise, you can see the counter will then change. See how the frequency is now gone a little bit higher because I've gone higher in frequency. So to have that counter work correctly, you need to have it somewhere on the peak of the signal. It does not need to be at the top. So again, putting the marker on the side right there does give us that 10 megahertz. So the instrument is reading, as expected. I've done some checking with it already, and I know that the amplitude is also accurate on here. So it's looking very good, no issues with any of that. So I'll turn the counter back off. Okay. Disconnect this. So now I'm going to grab this little antenna. So this is a little flexible antenna. Just connect that to the input right here. So the antenna is just sort of poking straight out towards the camera. So I'm going to tune in to a part of the FM band, a local station. So reach around over here. Let's do frequency. Make the center frequency. I'll go 98.1 megahertz. I know that's a local station that seems to be pretty strong that this can pick up. Okay. And the span, let's make the span 2 megahertz like so. Amplitude. Bring that up like so. I'm not going to put those peaks at the top. It'll cover up the indication right there. We want to see that for now, and it'll still work okay. So right now, actually, what you're seeing is that the center frequency is 98.1 megahertz. You can see that indicated down here. So this represents 98.1. You can see right there, that is that station. This is another station right here on a lower channel, and then another station over here on an upper channel. Okay. So if I take the span and actually go like so, there's 5 megahertz span. You can see all those peaks. Those all represent stations on the FM band. All right. So let's go back to the span. We're on that right now. I'm going to lower that down to 100 kilohertz. So we're still at 98.1 megahertz for the center frequency. That's where basically that marker is at, very, very close. to that value, but we want to demodulate this signal, okay? So again, now this is just 100 kilohertz span. If it's wider than that and we were seeing those other peaks of the other stations and I try and demodulate it, it'll jump around and you'll get various demodulation on the other signals. So I just want to stay on one station. So come over here, let's go to auxiliary control, demodulate, and FM demodulation, we'll turn that on. Okay. So the volume is set all the way down low right now, basically at 0. I just nudge the volume up a little bit. You can hear how that comes in very quickly, very loud. Also, let me make one other adjustment here. The demodulation time, let's make that 5 seconds. That'll demodulate for a longer period of time now. So again, watching this control right here, of course this volume control has, you know, a normal range of rotation, but if I barely turn it up a little bit, you can see I'm barely turning that control and it's very loud when that audio comes in. And that certainly doesn't seem right, because that range, I mean, to have that volume come up so quickly, it should be something that you turn this a little bit further and, you know, the volume would increase. If you turn this much beyond that, it's extremely loud. I would think it could even damage the speaker. So that doesn't seem right. So I want to take a look at that. Now, maybe this potentiometer is just dirty. So I'm going to try cleaning it first. I think maybe removing the bottom cover, it'll be right in this corner here. Maybe underneath here we'll be able to reach to that. If cleaning it doesn't help, then maybe there is an electrical issue going on. So, you know, one thing at a time, we'll start by cleaning it. I do want to get into the instrument and have a look around and just some general cleaning. I'm sure it has, you know, dust in it from years of use anyways. So I'll do that next, and then I'll reposition the camera, you know, when I have the instrument opened up, and we'll see exactly how the instrument looks inside and then what it takes to make this volume control work a little bit more reasonably, because this doesn't seem right the way it is. So I'll be back in a moment. All right, I have the case of the instrument removed, and you can see that's just sitting over here. So what would basically be the top and bottom covers all removed as one complete piece or assembly. The tilt handle and everything comes off all together. So I'll just move this out of the way. And as you probably would imagine, the instrument is absolutely packed with electronics inside. Very, very compact design internally, with many, many layers of circuit boards. So if I move this over a little bit like so, you can see there's hinges on the side right here. These allow these boards to tilt, so there's multiple layers of circuit boards, and these will hinge and tilt outward. And then up here on the top there's a diagram that shows how to open up those circuit boards. Position this like so. The unit is pretty heavy too. So you can get the general idea. You lay the instrument on its side, and then the boards tilt outward like so, which I will certainly need to do to gain access, you know, further into the instrument. Now I'm going to need to take a closer look and see exactly where the audio portion is for that demodulation control, because the potentiometer is a sealed design, so it's very unlikely that that potentiometer has any issues with it. I can see it. It's on the other side. A little bit hard to photograph with the camera, but you can certainly see it from this other side, looking down in here, but on the back side. But the potentiometer is all completely sealed up. There's no way to clean it. That's a good design and all, no problems with that. But unfortunately, it looks like there may be an electrical issue instead of just a simple cleaning. So I'll have to investigate that further. The first thing that I'm going to do, though, is to measure that potentiometer with the ohm meter and just see if it's actually working correctly or not. They only have 2 wires going to it. The third terminal is not used on it. So I'll do that check, and if that looks okay, then I'll continue to investigate further into the electronics. As far as cleaning inside, I haven't opened up the unit, of course, any further than what you see right now, but there's a little bit of dust, but it's not too excessive, so I'll clean the unit as needed. I'm noticing some dust around some of the vent openings and stuff on the side here, but pretty minor actually. It doesn't look too bad. There may be more inside though. We'll have to see how that looks. So I'll reposition the unit a little bit here and do some more work, and then I'll continue when I find out a little bit more. All right, I've done some cleaning inside the spectrum analyzer, so it's looking very good at this point. Most of the dust and lint was contained in the power supply section, which is right in here. That metal cover right there goes on the top of the power supply, so the air from the fan is brought in this way, directed over the power supply, and the heat sinks in the power supply, and then it goes out that direction over there. So it's all cleaned up. Most of the dust and lint was in that power supply section, to be expected. Now you can see the instrument is on its side, and then the circuit boards fold outward for access, inside. And you can see how they pivot on the back edge back there. There's some hinges, and they're all stacked up, so very dense construction. The other side of the spectrum analyzer has the same design. The circuit boards fold out in the other direction. But I did notice an issue in the power supply, so let me zoom the camera in a little bit closer here. Pardon the camera movement. Grab my flashlight here. So you can see in this corner right here, you can see those components that say X2 on them and then 100N. So those are 100 nanofarad X2 or X-class type safety capacitors, but the rating is X2. So those are the RIFA brand safety capacitors, RIFA, and above them there's two smaller capacitors that are the Y-class capacitors. I believe those are 2200 picofarad. So on the smaller capacitors, I can easily see a crack in the side of the capacitor. These larger X2 capacitors, I can't really see the side on those lower two, and that one it's a little bit harder to see as well, but I wouldn't doubt that they probably have cracks in them as well. And again, the smaller ones do have cracks. I can see that with no trouble at all. So what happens is on those safety capacitors, when they develop the cracks in them, moisture gets inside, and then they basically go off like little ticking time bombs, and they usually destroy circuitry and around them as well. I've had it happen numerous times in other devices that I own, other instruments and so on. These RIFA capacitors were widely used by many manufacturers in a lot of different devices. So at this point, when I see a RIFA safety capacitor, it gets replaced no matter what, and especially when you see cracks in the case. I've done some videos about the safety capacitors, what their purpose is, and also the RIFA brand, the failures and what happens on them. So again, there's videos that I've already done on that. So I won't really cover any more on that on this, but I will replace them, and in doing so requires removing this power supply. Let me zoom the camera back out a little bit here. So you can see this power supply is tucked away pretty tight in there. With the flashlight here, you can see quite a bit of wiring around it there. It's a high voltage module on the top up here. Some wiring that plugs in. So it's definitely tucked away down in here. There's some screws that need to be removed, and then that circuit board will come out. Now if those capacitors were okay and I didn't see any defects on them, this circuit board could be left alone. I wouldn't have to disassemble it any further, but I need to take that out so that I can desolder those capacitors. So I'll continue with doing that, and I'm also going to investigate where the potentiometer for the volume control connects in and do some checking on that circuitry. So I'll be back when I have an update and some more information. Alright, I have the power supply circuit board removed from the spectrum analyzer. You can see that sitting over here. And I've replaced the 5 safety capacitors on that circuit board. So I'll show you the old capacitors in just a moment. Now if you're following along and working on an instrument like this, you are doing so at your own risk. You need to be aware of the dangers involved with the high voltage on this circuit board, as well as the cathode ray tube, or the CRT, and this high voltage module right here. The CRT can retain a charge long after the instrument is powered down. The anode of this CRT operates at least 9,000 volts, and again that charge can remain for quite some time. The anode comes out under this metal shield. There's an opening over on the side over here, and then there's a rubber boot on the wire lead. But you need to know this correct procedure to discharge that anode before you're working on this area of the spectrum analyzer. There's also a direct AC line connection in this switch mode power supply over here. The AC line comes in this area over here, and these capacitors right here can retain a very dangerous charge. So again, if you're following along, you're doing so at your own risk. So be safe and take care. So to remove this power supply, because as you can imagine, it fits pretty snugly down in this area right here of the spectrum analyzer, you need to start by removing this high voltage module. There are 3 screws on that module, so that module sits on this area of the circuit board over here. So you remove those 3 screws. And then on the power supply itself, there's a screw right here and a screw that goes through the center of that heatsink, and then a screw that goes in this hole right there and right over there. So with that hardware removed, and then remove any of the cables that come into the power supply, so various connections over in this area. There's a large ribbon cable that plugs in over in this side, which is actually that ribbon cable right there. With all of that disconnected, you take the power supply, tip it upwards like so, and then lift it and out like that. So pretty straightforward to remove it, but a number of different things that need to be taken apart before you can get to that point. So here are the safety capacitors that were removed, and the larger capacitors, the 100 nanofarad, they look okay. I don't really see any serious cracks in the housings. However, they don't test so good on the Sencor capacitor analyzer, and I'll show you that in just a moment. They basically failed the test for leakage, so they are on their way out. They're not in very good shape, even though they look okay. The two smaller capacitors, if you notice on, let me see if I can get it to focus here. This capacitor right here, you can see under the REFA name, see that line, see that crack in the side right there? That capacitor is in pretty bad shape. See that line right along the side there? And this other one, it has some hairline cracks that are forming in it as well. This one's definitely more noticeable though. It's very common that these REFA capacitors start to develop those cracks, and then once that happens, moisture that's just naturally in the air gets inside the capacitor and then they completely fail. So definitely need to be replaced. Let me connect one of the capacitors over to the Sencor LC102, and I'll show you the leakage test and exactly how that capacitor failed. All three of the X2 class safety capacitors had excessive leakage. So I picked one of them, but they all had similar readings, and I'll demonstrate it on the Sencor LC102. So if we take a look at the capacitor value, you can see 0.1086 microfarad. So nothing wrong with that. So 0.1 microfarad is the same as 100 nanofarad, which is the marked rating on the capacitor. However, if we do a leakage test, so this is applying 250 volts to DC, you can see 0.31 microamps. It does drop a little bit. Still remaining though. And then it does show bad on the display. It does not pass the leakage test. You can see the leakage current remains, and that really should fall much lower than that. So that capacitor is becoming leaky, and when I say leaky, that's electrically leaky. It's basically turning into a resistor internally. Now let me grab one of the new capacitors, just like I installed. So we can see that right here. And these are modern production. Even though it says REFA on it, I have not had any issue with these current production capacitors. They seem to work very, very well. So if we do a capacitor value test, you can see 0.0981, so right at 0.1 basically, so no problems with the value. And if we do a leakage test, see, we have 0.17 microamps, 0.11, dropping down 0.06, and now it does say good on the display, 0.09. So you can see those numbers are definitely lower than that other old capacitor was reading. 0.08, 0.06, continuing to fall a little bit more, 0.05, and that's what we want to see. That leakage current should be very, very small. You can see it's basically falling near zero now, 0.02, 0.03 microamps. And that's exactly what we want to see. And that's applying 250 volts to DC to the capacitor. You can see that was basically getting almost down to zero. So the power supply should be good now for the long term with those new capacitors installed. And I'll continue on looking at the issue with that audio and the volume control. Before I put the top cover on the power supply, I wanted to check the voltage at these two test points where you see the probes connected. And the voltage at those test points should be the value that's written on a label on the end of the high voltage module. So in this case, the module is marked as 111.5 volts, and that's characterized at the factory. So every module is a little bit different, and the voltage that you set at these test points needs to be exactly what's on that label. So you can see at the end of the red test probe down there, there is a potentiometer on the circuit board. That's the only adjustment in the power supply, and that needs to be dialed in to exactly the voltage that's on that label. So that is where it is set now. So we'll come up here. Now originally it was reading a little bit high. It was about 111.9. You can see now it's dialed in 111.5, so it's spot on. And that voltage affects the high voltage module and ultimately the CRT voltage, which should be exactly 6 volts. So if that voltage is running high, the CRT will have a higher filament voltage, which you don't want. It'll shorten the life. So that's looking very good at this point, and we can continue on. Okay, now let's take a look at the audio amplifier section. As you recall, I mentioned that the audio from the speaker is extremely loud with the volume control just above its minimum setting. So a slight rotation of the volume control produces very, very loud audio. So let's see if we can figure out why that's happening. So we'll take a look at the schematic and see how the circuit actually functions, but I'll point out a few of the components that I'll be referencing on the schematic. So right here, this integrated circuit is U704 on the schematic. And the purpose of this integrated circuit is to select either the AM or FM demodulation signal. All right, so it's a digitally controlled switch. So there are several inputs to this integrated circuit, and then there's a common output. So the audio output from this chip flows through this capacitor right here, and it's applied to this integrated circuit over here, which is an op-amp. And that op-amp is U708 on the schematic. So that op-amp is configured as a buffer amplifier, basically a gain of 1. So the input signal and the output signal are the same. And then the signal from that amplifier is applied to the power amplifier, which is right here. So that integrated circuit is U707. Now, here's where there's a little bit of confusion. U707, as drawn on the schematic, is an LM386, which is an 8-pin device, but you can see this is actually a 14-pin device, and it's actually LM390. I suspect that this spectrum analyzer has a revision on the circuit board design that probably came after the schematic. Now, the LM390 and the LM386 are very, very similar devices. The package size is a little bit different. The pinouts, of course, are a little bit different, but the support components around them and how those audio amplifier chips function is basically identical between the two. The LM390 that's installed in this unit is a little bit higher wattage. I believe this device is a 1 watt output, and I think the LM386 has a little bit lower output power. So let's take a look at the schematic and see the details of how this actually functions, and then we'll take some readings on the circuit and see if we can find out exactly what's happening. Maybe there's a failed component or something's going on. So I'll turn the camera over to the schematic and we'll go from there. Here's the schematic for the audio amplifier. Now on the schematic you can see these triangle symbols. These are all common ground connections throughout the circuit. Okay, so those points are all tied together. Also remember that this device right here, the power amplifier, is shown as an LM386, but what's actually installed is an LM390. So this is an 8-pin device, but what's actually in the spectrum analyzer is a 14-pin device. So when I take some readings in the circuit, I'll just need to use the appropriate pins for what's actually installed. All of the support components around the device are identical, so I've looked and the values of all these capacitors and resistors are actually the same. Again, the LM386 and LM390 function very similarly, and they're set up the same way with the support components around them. Now, U704, which is that digitally controlled switch, isn't shown on this schematic, but it's off on the left-hand side over here, but the output of that switch is connected to this capacitor right here. So the audio signal is going through this capacitor, and it's being applied to this unity gain or buffer amplifier, this op-amp, U708. And the output of this amplifier is connected to the 7.5 k ohm resistor. All right. So the output of this resistor, you can see it comes over here and it goes to the input of the power amplifier. It also connects to this wire, and this wire is going over here. It goes off to this connector. This is the connector on the edge of the circuit board, but this is going to the volume control on the front panel. And the volume control is a variable resistance from this wire to this wire over here. And you can see this wire is returned back to ground. Okay? So we'll look at the volume control function in just a moment. I'll get back to that. But you can see on the other side of the power amplifier, this connection comes over here to this capacitor, and it comes over here. The speaker is from this point, and then the other side of the speaker is connected right here, which returns to ground. Now this capacitor is necessary because by design, half the supply voltage that's powering this device is appearing at its output, and that DC voltage has to be blocked from flowing through the speaker, otherwise it would damage the speaker. So this capacitor is blocking that voltage. These components right here form what's known as a Zobel network, this capacitor and this resistor. They're just stabilizing the output of the amplifier. And coming back over here, this capacitor is just a decoupling capacitor off of this audio line. You can see it's going to ground right here. So the volume control is a variable resistor, and when the volume is set to its minimum position, this line is connected directly to this line. And as you increase the volume to obtain a louder and louder audio signal, more and more resistance appears between these 2 points. All right. So what's happening is you can see this amplifier's output comes into this resistor, and then the other side of the resistor is coming over here, but it's being pulled directly to ground when the volume control is at its lowest setting. So this is coming over here and it's just going directly to ground. But this resistor prevents this amplifier's output from being shorted directly to ground. And as you increase the volume, more and more resistance appears across this point, and the input to this amplifier is essentially the midpoint between 2 resistors, so you have a voltage divider. So as the volume control is increased all the way to its maximum, you have more and more resistance across these 2 points, and more audio signal is allowed to appear at the input of this amplifier. Now, something that I want to take a look at right here, this capacitor and this resistor, you can see this ties to ground right here. These components set the gain of this amplifier. If nothing is connected, I believe on here it's pin 1, but it's between pins 2 and 6 on the LM390. But if nothing is connected, the default is a gain of 20. And as you add a capacitor or a capacitor and resistor, it increases the gain of this amplifier. So the way this is set up, we actually would want to be seeing a gain higher than 20. That's what's expected because of these components. Now, we seem to have a lot of gain. That's really the problem. The very little input signal going into this amplifier is creating a huge signal coming out. Now the other thing is that if the volume control is defective in some way, so we'll take a resistance reading and make sure that that's actually not happening, because if we're turning the volume control and its resistance is not as expected, that could certainly be a problem as well. So we'll look at the volume control to make sure it's functioning correctly. And also I will go through and check the various values of these components, the resistors and so on that we see here. And then let's take some readings of the audio signal, and we'll follow the audio signal from this point through this buffer amplifier over here. We'll watch the audio signal as the volume control is rotated, and then see what it is coming out of the amplifier. All right. So let me reposition things, and I will put a test signal into the spectrum analyzer, and then I'll grab my voltmeter and start with some troubleshooting. Here's the RF signal generator that I'll be using to troubleshoot the audio section in the spectrum analyzer. So you can see it's set to 300 megahertz. That value is not critical, it just needs to be something within the range of the spectrum analyzer, so I just picked 300 megahertz at random. And you can see it's set to frequency modulation, 20 kilohertz deviation, and it's going to generate a 400 hertz tone. That's what it's modulating with. So in the spectrum analyzer, in the audio section, we'll actually be measuring a 400 hertz audio signal. And then you can see the output of the RF signal generator is set to 100 millivolts. Okay, let's start by taking a resistance measurement on the potentiometer for the volume control. Now the volume control is a sealed type and it cannot be cleaned. It's very high quality, as to be expected from Hewlett-Packard. And I did take a measurement right at the back of the potentiometer on its terminals, and it seemed okay, but I want to take that same resistance reading right in the circuitry where the wiring connects, up on the circuit board, to make sure that there's no issue with the interconnecting wiring and so on. So we'll start with that measurement. Now, if you look at the schematic right here, the point that I'll be taking the measurement will be between this resistor and then the input of the amplifier over here. So it's this point where the wire goes off to the potentiometer. The other side of the potentiometer is grounded. So for this test and also for the voltage readings when we continue on, the negative lead of the digital multimeter is just connected to the chassis of the spectrum analyzer. All right, so let me grab the positive probe here and here like so. I'm gonna hold that there. All right, so we see 0.3 ohms. The volume control is down at the lowest setting. Start to increase that. I've just turned it a little bit. All right, it comes up. So right there, that's actually about where the audio is getting very, very loud. That's interesting. It's only 23 ohms at that point. I'm turning it slowly. It's increasing very nicely. No issues there. Continuing to rotate. 1K ohm. Continuing on. Still rotating, so it's continuing to increase. So I was just rotating it very slowly, and it seemed to increase, with no issue, and tops out there at about 17.5 K ohms. So no dropouts, no indication of any problems. Start turning it down. That jump there is just when the meter auto ranges. There, that jump again, that's no concern, that's not a problem. And then it's back to 0 again, lowest setting for volume. So I don't see any problem there. Those readings look perfectly fine. But it is interesting that the slightest little increase right there, right at that point right there, that's where the audio gets really loud. It's only at 23 ohms. Interesting. It's not that much resistance really. Remember that this is still, when this is down at that low resistance in 22 ohms or so, it's basically pulling that audio line down towards ground, with very low resistance. When you get up, let's say over here like that, where you have a little over 1.6 K ohm, that's where you'd expect the audio to get very loud. But at that point, that would be, just ear-piercing loud, if not destroying the speaker, given how it's operating. So again, when it's all the way down there, 0.3 ohms, no problem there with that. That's basically shorting the audio line to ground. All right. So I think we can safely say that the potentiometer is functioning properly, that there's no issue with that. So I'll go ahead and power up the spectrum analyzer. Take a moment to power up. It'll run its self-test. Then I'll connect the coax to the front panel, put a test signal in. We'll take some voltage readings in the audio amplifier section. I'll start over at that digital controlled switch, which is basically, for our purposes, where the audio signal is originating. At that point, we'll work through the circuit. Of course, the demodulated signal does originate prior to that chip, but there's no sense in going further back in the circuit at this point. So spectrum analyzer is about done with its self-test, I think. Yep, it's all set. So I'll connect the coax to the front here. All right, I have the spectrum analyzer configured with the test signal. You can see on the display over here, you can see that's the modulated 300 megahertz signal. So that's what an FM modulated signal looks like on a spectrum analyzer. It's a 20 kilohertz modulation with a 100 kilohertz span. 300 megahertz is right in the middle of that display. So if I increase again the volume control, you can hear that's that 400 hertz tone, all right, that it's being modulated with. So I'm going to increase that like so. Reach over here. So disregard the readings that you see on the voltmeter right now. I'll come in here. Okay, so 145 millivolts. Again, that's that 400 hertz tone. can see when the tone stops, how that dropped out, then it comes back again. The reason it comes and goes like that is because it demodulates for, I have it set for 10 seconds, then it sweeps again, then it demodulates again for 10 seconds. So the audio signal out of the digital switch is 145 millivolts. See that right there? Alright, so that's a reasonable value. So if we come over to that op amp, that unity gain op amp, let's look at its output, which would be on pin 1. And there it is. So it's exactly a unity gain, 145 millivolts. That's coming out of the op amp. So no issues there. Let's look at the other side of the resistor that is connected to the volume control. And let's see what happens when we rotate that volume control. I reach around here like so. Okay, so we can see the volume control when I'll go all the way down to 0 again. You can see it basically pulls that value very, very low. I'll increase that. It's getting very loud there, just to the point of some distortion, and you can see that very low signal right there. I mean, it's down in only a couple millivolts. Pretty loud tone right there, and it's 2.3 millivolts and some change. Okay, then it goes away, comes back again, 2.3. So that volume control, I've barely rotated it, and that makes sense because we saw that the resistance is very low, so it's shunting most of the audio signal to ground. Okay, most of that signal is being pulled to ground, so that 145 millivolt audio signal, only a few millivolts of that is actually getting through and being applied to the power amplifier. So on the LM390, the input is on pin 8. So let's take a look at pin 8. It's actually over here. Okay. The volume control is down low again. I'll increase the volume control. There we see that very low millivolt signal again. 1.7. 2 millivolts right there. So the same as we just saw at the other point that I was reading in the circuit, which makes sense. So with the volume control set where it is, which is just rotated slightly, we have 2 millivolts going into the audio amplifier. And that's producing a very loud tone at that point. Okay, now let's look at the output, which is at the speaker. It's actually larger than that needs to be there. Let's go down. So with 2 millivolts going in, we have almost 3/4 of a volt, 0.76. So very large amount of amplification going on there. So a 2 millivolt signal is being amplified to basically 760 millivolts. There is a lot of amplification going on there. Turn that down, you can see it goes away. If I bring that up just a little bit, barely nudge the volume control. Get a very small signal there. Very loud at that point, and again, that's barely rotating the audio control. So it looks like we have almost too much amplification going on with that power amplifier, because the input, given a very small audio signal going in, is producing a very large signal going out. If it didn't have so much gain in that power amplifier, then you would be able to apply more signal to it, meaning that the volume control could be rotated to a more usable range, and then the output signal would be, you know, just at a comfortable level. It's interesting because there's no adjustment in the circuit, and the gain is set by the components that are, you know, around that chip. There's a capacitor and a resistor that affect the gain. On the schematic, it looks like they have an 82.5 ohm resistor and a 22 microfarad capacitor, and those are in series and they're set connected to set the gain. I think what I should do, and actually you can see on the schematic here, those are the components that are over here. Okay, it's blurring a little bit, but that's where it is on the schematic. Those two, that resistor and capacitor right there. I think the next step would be to take that resistor, the 82.5 ohm resistor, and remove it and replace it with some little pins on the circuit board that I can clip onto, and then hook a variable resistor to it and kind of dial in some different values and see what effect that has, and see if we can adjust the gain, or if the gain is not adjustable, maybe the power amplifier chip has failed. You know, if the LM390 chip may have a problem, for that matter. So let me remove the resistor, the 82.5 ohm resistor. I'll put some little pins on the circuit board, and then I'll be back when that's done, and let's see if we can change the gain of the circuit. I don't know, the 82.5 ohm resistor seems like a very low value. I would expect that to be a little bit higher, because the lower the resistance on the gain adjustment, the higher the gain. So it would seem like that resistor should be a higher value, and I don't know why they would want so much gain in the circuit, because it's clearly too much, really. I mean, by the time you rotate that volume control up to even a quarter of the way rotation, it's, you know, causing distortion, and it's extremely loud, so it's really not usable in the range that it has right now. So let me make a little test setup here with that resistor, and then I'll be back and we'll continue on. Alright, I was able to change the gain of that audio power amplifier, and it is now working very well. So here's the little resistor that was in there. That's the 82.5 ohm resistor. There's nothing wrong with that resistor. It does test fine. However, in its place, you can see I have soldered in two little pins on the circuit board that those test leads are clipped onto right there. And then over here, you can see they're going over to this little potentiometer right there. So I'm able to dial in, you know, across the range of that potentiometer, so I can just adjust that and see the effect that it has. And it does, in fact, change the gain as expected. Let me zoom back out a little bit here. Go over to the meter so you can see the display. So now with the volume control, I'll turn the control up. So that's a comfortable level right there, and that's a good quarter turn of the volume control, if not a little bit more. Very easy to listen to level, no problems with that, but it could certainly go higher. And again, the volume control has a nice amount of rotation. It's not just real touchy at the beginning. Now, let me grab my meter probe here. So I'm going to turn this back up. So about that level there, and I will go to the input of the amplifier, which is pin 8. Okay, now take a look at the reading. We're at 16 millivolts. Okay, now before it was about 2 millivolts and we had extremely loud audio. Now we're at 16 millivolts and we're not having anywhere near the audio level. So much better range, meaning that amplifier now has a lower gain to it, and it puts that volume control within a better operating position and a better control over it. So it looks like it's functioning very well. What I need to do is measure that potentiometer and see exactly what it's actually dialed into, and You can actually see the effect here, or hear the effect, and then just choose the resistor based on its value. Come over here. You can hear that tone right now. If I change this setting, here it's getting louder. Goes down. Turn it back down again, so you can see that has an effect on the gain. So I'll play around with the setting on that to where it's comfortable, and I'll also demodulate just some normal voice type communications instead of just a tone, to make sure that it's comfortable for voice and just typical uses of the spectrum analyzer. And then when I'm happy with the setting that this potentiometer is at, I'll select a resistor that's the same value as whatever it's set to, and I'll solder that resistor in on the circuit board, and I'll let you know what that value is when I go ahead and choose that component value, but I don't know yet because I need to dial this in. So I'll do that next, and then I'll let you know what the final choice is. Alright, so it looks like 4.7 k ohms is a good value to go with. That works very well in the circuit. So I have a 4.7 k ohm resistor right here, and that's the resistor that I'll solder back onto the circuit board. So just to compare, this is the original 82.5 ohm resistor, and you can see right now this is set to a local FM station. I have an antenna connected to the end of this coax, so it's demodulating this FM station. It's on 98.1 megahertz. So you can see the volume control if I barely rotate it right now. Very loud with just a little bit of rotation right there. Okay, so now I will switch this resistor out to the one that I'm going to use. Okay, so in the circuit, now we can see the volume control has a much better range. Okay, much better. You can see how I'm rotating that, and it's a much more usable range that you can rotate that control through to get the audio. So very happy with that result. That's working very well at this point. So I'll get this resistor soldered in and get the spectrum analyzer put back together again. And it looks like this job is complete. The Hewlett-Packard 8561E spectrum analyzer is now completely reassembled, so it's ready to put into service on the bench. If you enjoyed this video, please give it a thumbs up. And if you're enjoying the videos on this channel, remember to hit that subscribe button down in the lower corner. There'll be many more videos like this coming in the near future. So until next time, take care. Goodbye for now.